In this lecture, we will discuss about the step response of second order control system. The generic form of a second order control system is given here, which is C of S upon R of S is equals to omega n square divided by S square plus 2 zeta omega n of S plus omega n square. We have already discussed the poles of this transfer function. They are located at minus omega n of zeta plus minus under root zeta square minus 1. Now, based on the value of this zeta, we can have four different cases. Case number 1 is if zeta is greater than 1, then the two poles of this transfer function, they will be real and your system will be overdamped. In that case, if you plot these two poles on your S-plane, your poles will be located somewhere here. Let us assume minus A is one pole of this equation and minus B is second pole of this equation for underdamped case. The second case is if zeta is equals to 1. If you put zeta is equals to 1 in this equation, this term will become 0. Okay? And there will be a second order pole at minus omega n of zeta. Here zeta is already 1. So, in case number 2, you will have two poles at the same location, that is minus A. Case 3 is if you put zeta is equals to 0, then the poles of the transfer function will be purely imaginary and your system will be an undamped system. The poles are minus omega n of zeta plus minus omega n under root zeta square minus 1. So, putting 0 in place of zeta, then this whole term will become 0 and this will be an imaginary number which we are representing by j. So, in case number 3, the two poles of the system will become plus minus j omega n. If you plot these two poles on the S plane, then the location of the poles will be on the imaginary axis. One pole will be here and another pole will be here. Case number 4 is if you put zeta less than 1 in this equation, then what is going to happen? The poles of your system will be complex. That is, you will have a real part and an imaginary part. So assume zeta is less than 1 in this equation. Then it means that you are always going to get this number in imaginary form. Okay? So, rather than representing it by a real number, we have put j here by transforming or by changing 1 with positive 1 and the positive zeta square with negative zeta square. In that case, you will get j here and these two poles, they are representing complex number. Okay, and if you want to plot these two poles on the S plane, then the location of the poles will be like this. They will be complex conjugate poles. Let us find out the step response of the second order control system in underdamped case. Underdamped case means that your zeta will be less than 1. Okay, once again, we have this generic form of a second order control system transfer function, that is C of S upon R of s is equals to omega n square divided by s square plus 2 zeta omega n of s plus omega n square. Since we are dealing with an underdamped system, the poles will be complex. Okay, in that case, the poles of this transfer function will be minus zeta omega n plus minus j omega n under root 1 minus zeta square. We have already discussed this previously, that how we have represented the poles in this form. Since zeta is less than 1, okay, we can also write these poles as minus sigma d plus minus j omega d, where sigma d is the damping factor and omega d is the damping frequency. So we have this equation 1. Now this is our equation 1. In factored form, we can write this equation as C of s upon R of s is equals to omega n square divided by s minus p1 into s minus p2. So rather than writing this denominator of equation 1 in polynomial equation, we are actually writing equation 1 in factored form, or the denominator. We have actually written the denominator in factored form. Now P1 is actually pole 1 and P2 is pole 2. So we can simply put the values of poles here to come up with this equation. Okay, so here we have simply put minus sigma d plus j omega d here and minus sigma d minus j omega d here. Now the next thing is, how do we find out the step response? I have drawn the block diagram of this transfer function. Now this is our output, this is our input. Okay, in terms of block diagram, you apply the input at this side of your block and this will be your output, and this is the transfer function which is representing this equation. So if you want to find out the step response, it means that you need to apply the unit step signal at this point. I think we already know that unit step signal is represented by u of t. This is our unit step signal. Since we are working in Laplace domain, it means that we have to use the Laplace form of our unit step signal. This is the Laplace transform of the unit step signal. So I have actually written equation 2 here by actually moving R of s here. Okay, so after moving R of s on the right hand side, your equation 2 can be rewritten as C of s is equals to R of s multiplied by this term. Okay, then I have actually put the value of R of s, which is 1 upon s here. So this is actually the equation you have to use to find out the step response. In the next step, we need to solve this equation using partial fraction expansion. Using partial fraction expansion, we can write C of s as a upon s plus b upon s plus sigma d minus j omega d plus c upon s plus sigma d plus j omega d. The original equation was this. So after using partial fraction expansion on this equation, we have written it in the form of this. So in the next step, we need to find out what is A, B and C here. Now, solving this equation, I have found A is equals to omega n square divided by sigma d square plus omega d square. Then I have found B equals to this term and C equals to this term. You can solve by yourself to find out whether the values of A, B and C found here are correct or not. That is your homework. Now, taking the inverse Laplace transform of equation 3, we can write this equation in time domain form as C of t is equals to A u of t. Now, in equation 3, the inverse Laplace transform of A upon S is A into u of t. This is your unit step signal. Then the inverse Laplace transform of this second term is B e raised to the power minus bracket sigma d minus j omega d into t. The inverse Laplace transform of this third term in equation 3 is given here. Now, this is the step response of your system in underdamped case. The only thing which is left is replacing sigma d and omega d with their actual values. So, we know that sigma d is equals to zeta omega n and omega d is equals to omega n under root 1 minus zeta square. So, putting the values of sigma d and omega d here, we can write the step response of the second order underdamped system as A u of t plus B e raised to the power minus zeta omega n minus j omega n under root 1 minus zeta square into t plus C e raised to the power minus zeta omega n plus j omega n under root 1 minus zeta square into t, where A, B and C, they are given here. So this is the final equation for the step response of the underdamped system. Let us find out the step response of undamped systems. We know that in the case of undamped systems, zeta is equals to 0. We already know the step response of the underdamped system, which is found to be equals to this equation. Now, if you need to find out the step response of undamped system, you simply need to put zeta is equals to 0 in this equation. So, if you put zeta is equals to 0 here and here, here and in this part, then your equation, you will come up with this equation, and this is the step response of your undamped system. You can put the values of B and C here to further simplify it.